You plug a laptop into a wall jack, and it just works. It gets an IP address, a default gateway, a DNS server, everything it needs to reach the internet. No one typed anything. No one had to. That automatic address assignment is DHCP, the Dynamic Host Configuration Protocol, and it's the reason modern networks feel effortless. Without it, every device on the network would need someone to manually configure its IP settings, and in a company with thousands of devices, that's a nightmare. Every device that needs to communicate over a network requires 4 things at minimum: an IP address, which is the device's identity on the network; a net mask, which tells the device which addresses are on its local network and which are not; a default gateway, which is the router the device sends traffic to when the destination isn't local; and a DNS server address, which translates domain names into IP addresses. DHCP delivers all 4 automatically. It works on a client-server model. The client asks, the server answers with a lease. DHCP is stateful. The server keeps track of which addresses it's handed out and to whom. This is different from SLAAC in IPv6, which is stateless and has no server tracking anything. When a device first connects to a network, it has no IP address and no idea where a DHCP server might be. So it starts a 4-step handshake called DORA. D for discover, O for offer, R for request, A for acknowledge. The client sends a discover message as a broadcast, source address 0.0.0.0, destination 255.255.255.255. It's essentially shouting into the network, anyone out there have an IP address for me? The DHCP server hears the broadcast and replies with an offer message, proposing a specific IP address along with the netmask, gateway, and DNS settings. The client then sends a request message, also as a broadcast, confirming it wants that address. Broadcasting the request serves a purpose. If multiple DHCP servers offered addresses, all of them hear which one the client chose, so the losing servers can release their offered addresses back into the pool. Finally, the server sends an acknowledge message, confirming the lease. The client can now use its IP address. DHCP uses UDP as its transport protocol. The server listens on port 67, and the client listens on port 68. Both ports are reserved, unlike most protocols where only the server uses a reserved port. Remember these for the exam. DHCP server is UDP 67. DHCP client is UDP 68. The address you get from DHCP isn't permanent. It's a lease, and lease times vary. A home network might give you 24 hours. A coffee shop Wi-Fi might give you 30 minutes. When half the lease time has passed, the client sends a unicast request directly to the server to renew. The server replies with an acknowledge, and the lease clock resets. If the client can't reach the server, it keeps trying until the lease expires. Now let's talk about configuring a Cisco router as a DHCP server. In a small network, the router is usually the DHCP server. Your home router does this already. The first thing you do is exclude addresses you don't want the server handing out. Servers, printers, and other devices that need a constant IP should be statically configured, so you exclude their addresses from the pool. The command is IP DHCP excluded-address, and it goes in global configuration mode. You specify a range, like 2 through 5 in the 10.0.0 network. You don't need to exclude the network address, the broadcast address, or the router's own interface address. The router already knows not to lease those. Next, you create the DHCP pool with IP DHCP pool, followed by a name. This puts you in DHCP configuration mode. Inside the pool, you specify the network with the network command and either a prefix length or a net mask. Then you set the default gateway with default router and the DNS servers with DNS-server. Those three are the essentials. You can also set the domain name with domain's name and the lease duration with lease, specifying days, hours, and minutes. The default lease is 24 hours. You can also set lease infinite for unlimited duration. After configuring the pool, you verify with show IP DHCP binding, which lists all active leases, the client's IP, MAC address, lease expiration, and the client ID. The client ID is how the server distinguishes between clients. It's typically the hardware type prefix 1 followed by the MAC address. If you need to clear leases, you use clear IP DHCP binding with an asterisk for all or a specific IP address. Before the server hands out an address, it checks for conflicts. It pings the address it plans to lease. If something replies, that means another device is already using that address. Maybe someone manually configured it without excluding it. The server marks it as a conflict and removes it from the pool. You can check conflicts with show IP DHCP conflict and clear them with clear IP DHCP conflict once you've fixed the underlying problem. Network infrastructure devices, like routers and switches, typically use static addresses. They're easier to manage when their IPs don't change. But there's one common case where a router uses DHCP, the ISP connection. When you connect to your internet service provider, the router's outside interface is configured as a DHCP client. A single command on the interface, IP address DHCP, and the router gets its public IP address and a default route from the ISP. You can verify with show IP interface to confirm the address was learned via DHCP, and show IP route to see the default route. Notice the route code S, which normally means static, but in this case, it's a DHCP learned route. That's a Cisco iOS quirk. In larger networks, you don't want every router running its own DHCP server. Instead, you use a centralized DHCP server, a dedicated server that handles all address assignments. But there's a problem. DHCP uses broadcasts, and routers don't forward broadcasts across subnets. So how does a client on one subnet reach a DHCP server on another? The answer is DHCP relay. You configure the router's interface facing the clients with IP helper address, followed by the DHCP server's IP address. Now when a client broadcasts a discover message, the router intercepts it and forwards it as a unicast packet to the remote server. The server's offer and acknowledge messages come back through the router to the client. Make sure you put the helper address on the correct interface, the one connected to the clients, not the one facing the server. You verify it with show IP interface. Finally, the CCNA expects you to verify IP settings on actual client operating systems. On Windows, you use ipconfig for basic settings, and ipconfig/all for detailed information including MAC address, DHCP server, and DNS. To see the routing table, you use netstat with the RN flags. On macOS, the equivalent of ipconfig is ifconfig, which shows the IP address, netmask in hexadecimal, and MAC address. The routing table command is the same, netstat with RN flags. On Linux, some distributions still use the older net tools with fconfig and route. Others use iproot2 where IP-addr replaces ifconfig and IP route replaces route. The key is knowing where to find the IP address, netmask, MAC address, and default gateway in each output. That covers DHCP from the client's perspective through the server configuration, relay, and verification on multiple operating systems. The core idea: DHCP automates address assignment through a 4-step DORA handshake. Cisco routers can be DHCP servers with pools and excluded addresses. Relay bridges subnets with a single helper address command, and you verify settings with OS-specific commands on Windows, macOS, and Linux.